We talk about the concept of a resistor before we advance in this concept of resistor and electromotive force. So what is resistor? I've given the definition already. Now, and electromotive force is actually the work done in moving a unit positive charge from one point to another point, all right? So material defines from one point to infinity, okay? So we can also define electromotive force. So I'm defining electromotive force. What's electromotive? EMF can also be defined. Electromotive force to be the potential difference between the external and the internal resistor of a circuit, okay? You can either define it as the work done in moving a unit positive charge from one point to another or from one point to infinity, or you can also define it as the potential difference across the external and the internal resistor of an electric circuit. Potential difference between the external and the internal of internal resistor of an electric circuit. So you have E is equal to capital letter V, which is the external resistor, then small letter V is the internal. Okay, so this is your electromotive force. So you have E is equal to your capital letter V is given to be IR, all right, while small letter V is the lost voltage is given to be I small letter R. So at the end, what do you have? So you have E is equal to your capital letter V, which is the external potential, is given to be IR. Then the lost voltage is given to be small letter V. Meanwhile, if you're to determine the lost voltage, your electromotive force is measured in potential, so you can just do E is equal to V plus small letter V. Then you have E minus capital letter V is equal to lost voltage, or lost voltage is equal to electromotive force minus potential across the external resistor of the circuit. So, right, this lost voltage. All right, but if that is not the case, okay, you can determine the external too. Of course, this lost voltage is going to be I small letter R is equal to E minus the capital, right? Or you can express it as IR is equal to E minus I capital letter R. So because V is equal to I, capital letter V is equal to I small letter capital letter R. So that's how to express it. IR is equal to E minus IR. Then you can go with that format. And any other constant you're asked to find, you can make the sort of formula in terms of what you're looking for and give them the value. So that's the case, but that's not what I'm going to. So once my E is equal to IR capital, that is the external resistor plus the internal resistor, which is I small letter R. So I have E is equal to IR plus the lost voltage, which is expressed as what? The internal resistor. So this external resistor, this internal resistor, and the current are the same all through. So I'm going to be having my electromotive force to be I, open bracket, I have R plus R. That means if I want to determine current when you have two different resistors, I'm going to be having I into I open bracket R plus R. So I'll divide both sides by R plus R. I'll divide both sides by R plus R. So at the end, what do I have? I'm going to be having a value, all right, of I have R plus R here. That is what I, all right, I have E over R plus R is equal to I, or I is given to what? E over R plus R. That is what I have as current in electromotive force. So you can use that to determine the value of the current. And your values, all right, your electromotive force can also be arranged in series and in parallel. Okay. Now you can have their symbols in cells too, all right, just like capacitor. It can be arranged in series and in parallel as well. In series and in parallel as well. So if you are talking about a series connection, okay, this one is going to happen in the electromotive force. So you have a series like this, you have something of this nature. So you have your cell here, this electromotive force in series, all right. But if it's in parallel, this is series connection. If it's in parallel, they are going to be having something of this nature. You have something like this, you have something like this, you have something like this, you have this, and you have this, all right. So this is what? This is a parallel connection, all right. So you can do all to check the effect of the series and parallel connection, but I think if it's in series, your E is equal to E1 plus E2 plus E3, and your small letter R, if it's in series, R is equal to R1 plus R2 plus R3. Okay, in series, sum of the total of the net EMF is sum of the individual EMF, E2 plus E3. Then your R in series is given to be R1 plus R2 then plus R3. All right, and also this is series connection, and also in series connection, your value of the current, I think, are the same. the value of the current are the same in series connection. So you can check what happens at the parallel connection. Quite important. So that is that. Then when you now come to resistor, all right, this is just a brief work on EMF. I don't have a question here that I easily can pick, all right, but you should do your findings on that, all right, for the parallel connection. This E1, this R1, this E2, this R2, this E3, and this R3. This one is E1, this R1, this E2, this R2, and this E3, and what? And R3. So basically that's how to go about that. Okay, so now when you are talking about resistor, so let's look at what happened at the resistor once I've given the definition of EMF and the values that holds for that. Okay, so let's talk about resistor quickly. Now your resistor can also be arranged in series and parallel connection. All right, in series and parallel. So for series, what are we going to be having? For series, I have these values 2, I have 3 here. This is what happened at series connection in resistor. Then for parallel, okay, so this series, this R1, this R2, and this R3. Okay, so that is that. Then my V is equal to IR from Ohm's law. All right, so I'll talk about Ohm's law and would move on. All right, so I said that these are ourselves in what in these are EMF in series and parallel, and if it's in series, your the total EMF is sum of the individual EMF, and your internal resistance is sum of the individual resistance. So then for resistor, okay, your V is equal to IR from Ohm's law. What is Ohm's law? Ohm's law states that the current passing through a metallic conductor is directly proportional to the potential, provided the temperature and other physical conditions, even the current, are kept constant. So if it's from that place we got V is equal to IR, the law says that the current is proportional to the potential. In other words, V into what? Into I. All right, and resistance is constant, so you have V is equal to what? IR. All right, so V is equal to IR, or I is equal to voltage over resistance. All right, is what we got as what? As current in what? In Ohm's law, voltage over resistance. So our current is measured in ampere. Okay, current is measured in ampere. Potential is measured in voltage. All right, voltage, and your resistance is measured in ohms. Voltage V, and your resistance is measured in ohms. Resistance is in ohms. Ohms. All right, so that is what we have. Okay, so basically, let's quickly see the analysis on the series and the parallel connection of the resistor quickly before we end the video. Okay, so now when you talk about the series arrangement of a video of a resistor, now that's what we have on the board. Okay, so what's going to happen? You are going to be having you have your V is equal to IR. All right. So if you are having, how many resistors we have? We have 3 different resistors in this place. So if you are doing V, meanwhile the connection in series, when your resistors are connected in series, the potentials are different, but the currents are the same. I'll come again. Anytime your resistors are connected, all right, in series, potentials are different, but what currents are the same. Voltage V are the same. V is equal to V are different plus V2, all right, V3 to V infinity. While the current are the same, is equal to I1 is equal to I2. So let's use that. So if our voltage are the same, so to do for that, so we have VT is equal to V1 plus V2, then plus V3. Okay, so this VT will give us IR, then in total is equal to what is VI? VI will give us IR1 plus what is V2? V2 will give us IR2, then V3 will give us what? IR3, then everything to what? To IR infinity. Okay, so if that's what we have now, once our voltage are different, and we said that our current are the same, if current are the same also, so we have current into RT is equal to, we can put current outside, then we have R1 plus R2 plus R3, all right, everything to what? R infinity. Then at the end, current is going to cancel current, so we have R2 is equal to I into R1 plus R2 plus R3 into R infinity. So we have at the end of the day, all right, I go with I, then we have R total is equal to R1 plus R2 plus R3 into R infinity. Okay, this All right, connection is what we call a series connection, R series. So we have series connection of a resistor is equal to R1